You know that feeling, right? You're searching everywhere for your keys, tearing the house apart, only to realize they were in your pocket the entire time? Well, what if physicists are doing the exact same thing, but for, 85% of the entire universe? A pretty wild new idea suggests the answer might not be some missing thing, but something hidden in the very rules of space itself.
So, for about 50 years, the standard story in cosmology has been pretty clear. The universe is mostly filled with this invisible stuff called dark matter. It's the cosmic glue that's supposed to be holding entire galaxies together. We have built these massive, mind-bogglingly sensitive experiments to find it, but after all this time, we've got nothing, zilch, which leads to a really provocative question. What if the reason we can't find it is because, well, it was never there in the first place?
Okay, so before we dive into that radical idea, we really need to understand why scientists even came up with dark matter. I promise you, it wasn't just some wild guess. It felt like a necessary solution to a truly massive cosmic puzzle. I love this quote because it just perfectly captures the sheer frustration of it all. You see, we see the effects of dark matter everywhere. It's like seeing footprints in the snow, but you can never ever find what's making them. We see stars on the edges of galaxies moving so fast they should just fly off into space. We see light from distant stars bending as it passes through seemingly empty regions. The evidence that something extra is out there it's just overwhelming.
So the leading theory, the one that's been the front-runner for decades, is that this something is a whole new kind of particle. Think of it like invisible scaffolding for the universe, providing all that extra gravity needed to build the galaxies and cosmic structures we see today. It's a simple, pretty elegant idea. There's just one tiny problem.
We just can't seem to find it, and believe me, we have looked for decades. We've built detectors deep underground, shielded from all cosmic noise. We've smashed particles together at the Large Hadron Collider, hoping to just create one by accident. We chased these particles called WIMPs for years, and now we're looking for even more exotic things like dark photons. And still, the ghost remains a ghost. And now our brand new telescopes, they're sending back data that makes the whole ghost story even harder to swallow.
Okay, so this is where the story gets really, really fascinating. The James Webb Space Telescope is basically a time machine. It's peering back to the very dawn of the universe, and the pictures it's sending home, well, they don't quite fit the standard dark matter narrative. Webb is looking at the baby universe, just a few 100 million years old, and it's finding galaxies that are already enormous. They're huge and fully mature. That's a huge problem. Our models say that dark matter acts like a slow cooker, patiently gathering gas over billions of years to build a galaxy. What Webb is seeing is more like a microwave dinner. These things formed way too fast. It's like finding a fully built skyscraper just a few years after the city was founded. The timeline just doesn't add up.
And then, to make it even weirder, we have the complete opposite problem. Astronomers have found these very strange, almost transparent galaxies that seem to have little to no dark matter at all. I mean, none. If dark matter is the essential scaffolding you need to build a galaxy in the first place, how on earth do you build one without it?
So, you get all these contradictory puzzle pieces. What do? This is where science gets really fun. It forces us to ask a really deep, fundamental question. Are we just missing a piece of the puzzle? Or are we trying to solve it using the wrong rulebook entirely?
And this is where a bold, and I mean really, really bold, new idea comes into play. What if the problem isn't a missing particle, but a fundamental misunderstanding of space itself? This is the core idea behind a framework called quantum geometry dynamics, or QGD.
For more than a century, since Einstein, we've pictured spacetime as a smooth, continuous sheet of fabric that can be bent and warped. QGD says, let's throw that out. It suggests space is actually pixelated, made of tiny, fundamental, indivisible units. Just like the screen you're looking at is made of pixels, QGD argues that reality itself has a base resolution you can't go below.
Now, the key here is QGD's whole approach. It's what's called an axiomatic theory. All that means is that it starts with just a couple of simple bedrock assumptions, like space is pixelated, and then tries to logically build all the physics from there, without adding extra stuff later. And you can imagine, if you change something as basic as the nature of space, the rules you get for a force like gravity, well, they turn out to be radically different.
So here's the million-dollar question. If QGD gets rid of dark matter, how does it explain all those observations that made us believe in it to begin with? It does it by completely redefining the most fundamental force in the cosmos.
QGD's model of gravity is, well, it's pretty wild.
First, it suggests gravity is instantaneous. Its effects aren't limited by the speed of light. But here's the real trick. It acts differently at different distances. On the scale of a galaxy, it's attractive, providing that extra gravitational tug that keeps stars from flying away. That explains the dark matter effect without any actual dark matter. But then, at truly vast cosmic distances, that same force flips and becomes repulsive, pushing everything apart.
And right there, that is the beautiful part of this idea. QJD tries to solve two of the biggest mysteries in cosmology with a single key. The attractive part of its gravity mimics dark matter, and the repulsive part, that mimics dark energy, the thing causing the universe's expansion to accelerate. So instead of inventing two separate, mysterious things, it just proposes one new rule for gravity that could potentially explain both. It's an incredibly elegant solution. If, and it's a big F, it's right.
But hey, elegance is not enough in science. For an idea this radical to be taken seriously, it has to do more than just sound good. It has to make specific, unique predictions that we can actually go out into the universe and test.
This really gets to the core of how science works. A theory is only as good as its ability to be tested and, more importantly, its ability to be proven wrong. So, what are the testable claims? What could actually prove or disprove QGD?
And QGD makes some really bold predictions that are totally different from standard physics. For instance, it predicts that light might actually travel at slightly different speeds depending on which direction it's going. It predicts that photons, particles of light, actually have a tiny, tiny amount of mass. And it says that pulsars orbiting the supermassive black hole in our galaxy should behave in a very specific way that's different from Einstein's predictions. These aren't just philosophical ideas. They are things we could potentially measure.
Now let's be crystal clear here. QGD is a hypothesis. It has not been proven. It is way outside the mainstream of physics today. Its real value, right now, isn't about being correct. Its value is in challenging our core assumptions and forcing us to think creatively about the puzzles the universe keeps throwing our way.
And that brings us to the final thought. This whole frustrating search for dark matter has shown us that there are definitely cracks in our understanding of the universe. So what's the answer? Is it an invisible particle we're finally about to catch, or is it a fundamental rewrite of the laws of space and gravity? Whatever it is, the search itself is what drives science forward. The mystery of what's out there in the dark is forcing us to see everything in a new light. The only question is, are we ready for what we might find?